called ABCpy. Please go ahead, Lorenzo.
Hi, so hello everyone. I'll try sharing my screen and see if everything works the way it should. Cool, so can people see my screen now? Hello, can you see my screen?
Yes.
Okay, great. So yeah, thank you very much everyone. Good morning or good afternoon, wherever you are. As the presenter said, I am going to present the Python library ABCpy, which is again a library for likelihood-free inference. I will give examples basically of how we can define a model and perform inference with ABCpy, and I will also show how ABCpy can be easily extended to test new inference schemes. So just a quick recap. I think this was already mentioned before. So if you want to do approximate Bayesian computation, you need to define basically four main components. One is the probabilistic model from which you need to be able to simulate. Then you have a statistics and a distance functions. And finally, you have the ABC inference algorithm you want to use. So with ABCpy, we implement this kind of structure in an object-oriented fashion. Okay, for people who are familiar with R as four classes, this is basically the same logic as the R as four classes. So you have, with ABCpy, you have objects of the type probabilistic model, which implement a forward simulate method, which allows to generate simulations from the model. Then you have objects of the type statistics and distance, which again, they have a method called statistics and distance. And finally, the algorithms are implemented in objects of the type inference method. And these objects have a sample method, which allows to perform the inference itself. Right, so Bayesian synthetic likelihood and other related methods, which instead aim to directly approximate the likelihood, have a very similar conceptual structure as well. So you see still you have a probabilistic model, you still have a statistics. And the difference here is that you need to replace a distance class with an approximate likelihood class. And this approximate likelihood class will take care of computing or rather estimating the likelihood from simulation from the model. And still, of course, you need to have some inference method with which to perform inference. So I think I thought I'll start with a very minimal ABCpy example. So I will consider here a rejection ABC with a normal model, and I will show how you can use ABCpy to implement this and to perform inference. So first of all, of course, you need to define, we have a normal model which has two parameters, which are the mean mu and the standard deviation sigma. And we define priors for the parameters. So you need to import the distributions from ABCpy library, and then you just define the priors with these two lines. I'm using here uniform priors just for the sake of simplicity. Then you need to define the model, which is quite easy. You see, you define a normal model, which takes as inputs the mean and standard deviation. So next, what you need to define is the summary statistics, which are used for ABC. So for this very simple example, I'm just using the identity summary statistics, which just means I'm using the full data set, which in this case is actually just univariate to perform inference. So next, what you need to define is the distance. Again, in ABCpy, we implement some distances I will describe later, but here for the sake of simplicity, I'm using the standard Euclidean distance. And finally, what you need to define is also a backend object, which is used for parallelization if needed. So again, for this very simple example, I'm just using the dummy backend, which means no parallelization at all is used. So the last, that's probably more important step is defining the rejection scheme, the rejection ABC scheme, and using it to perform inference. So you see the rejection ABC scheme as well as an object-oriented framework. So you need to instantiate it with this line here. So you need to instantiate the rejection ABC scheme, pass into it the model, the distance class, the distance object which you define, and the backend. And of course, you can also pass some random seed to ensure reproducibility of random number generator. So finally, once you define that, you can perform inference by just calling the .sample method of the sampler. And you pass to it the observation, which we define here to be 180. And then you need to set the number of samples and the tolerance threshold you want to get from this rejection ABC scheme. So let's try to run this and see what happens. So you see this is now running, and the results will be stored in the journal file. Hopefully it will be done soon. Yeah, you see it's done now. So this journal object, as I said, stores results. And for instance, we can use this journal file here to print the number of simulations we use and to plot the posterior distribution. So you see here, this regression ABC scheme used about 6,000 simulations. And here you get this kind of posterior distribution, which of course is obtained with KDE from the samples. Right. So now I will have a quick look at the contents of ABCpy more in detail. So this table of contents is referred to version 0.6.2, which was released like 1 week ago or less. So besides the regression ABC scheme, which I showed before, we have a range of sequential ABC methods. And the reason why we are using sequential ABC methods is that they are very easy to parallelize across, let's say, particles. So we implement the population Monte Carlo ABC. We have sequential Monte Carlo ABC. Actually, we have 2 versions of it. And then we have 4, let's say, more recently proposed methods. So all of these ABC algorithms can be used with these following ABC distances. So we have the Euclidean distance, the standard one, standard choice. We also have the classification accuracy distance with logistic regression. And finally, we have divergences between datasets, which we recently added. So for instance, we have the Basset distance, the Kullback-Leibler divergence, and some others, which you can see here. Yeah, as I mentioned before, we also implement some methods for approximating the likelihood function. So we have the Bayesian synthetic likelihood and its semi-parametric version, which was described in the first talk very well. Then we have this ratio estimation one with logistic regression. And these 3 methods can be used with these following samplers. We have the standard Metropolis Hastings MCMC, and we have population Monte Carlo. So yeah, additional features of this library is parallelization across model simulations, and we use MPI and Spark to parallelize, and these 2 allow to scale to a high-performance computing cluster or supercomputers, for instance, as well as like standard research groups, computing servers, or stuff like that. So we also have ways to learn summary statistics, which optionally use neural networks. I will show this later in an example. And finally, we have model selection with random forests. Right, so I think I will dive now deep into how we can implement a model class. So the example I will show is taken from this repository, which is called ABCpy models, where we store a large selection of models which are commonly used in like ABC or likelihood-free inference studies. So every model has to implement, every model is defined through a class and has to implement 5 methods. So you have, of course, an initialization method. You have the forward simulate method, which I mentioned before, which is needed for generating simulations from the model. And then you have 3 helper methods, which are basically used to check during the inference whether everything works correctly. So let's have a look now. I'm using here as an example the Ricker model, which probably many of you will know is a very commonly used example in ABC inference. And as you see, I need to define a class here, which in order to define the Ricker model. And this class needs to take as a parent classes the probabilistic model and the continuous model classes. Right, so once you do that, you need to initialize, to set an initialization method, which in Python is called init in this way. And this initialization method needs to take as an argument, say as a mandatory argument, needs to take the parameters of the model. Then for this specific model here, we also pass to it the number of time steps we use in the inference, as well as a name which we give to, which is used in to store the model in the journal file. So you see the parameters here, which we pass at the initialization, are passed to this input connector object, which is used to define a graphical model of the hierarchical, let's say, prior structure. So once you do that, you need to initialize the model by calling the initialization of the parent class by this line here, which is just so that everything works correctly. and then initialization is done. So next method you need to implement is the forward simulate one. So in this one, to this one you need to pass a list with the input values for the models. You need to pass the number of forward simulations which you want to get for that set of parameter values. And finally, you also need to pass a random number generator, which you can use inside the forward simulate method to perform, to draw random numbers. And by passing this number here, by defining this argument here, you ensure reproducibility is maintained. So inside this forward simulate method here, what you need to do is basically use the parameter values which you pass in this input values parameter, and use them to draw that the specified number of forward simulations from your model. So in this case, I'm not putting the full code for simulating the Ricker model. I've defined a function somewhere else because otherwise it would be a bit too long. But what I do here, you see, I define an empty list, which has num forward simulations elements, and then I have a very simple, very stupid loop over the number of forward simulations, so that for each step of this loop, I generate a simulation and I store it in this list. And finally, I return the list from this method. So of course, instead of using this stupid loop, you could also, if your model is capable of vectorizing, you could also vectorize the forward simulations, which is very helpful if you need, for instance, to use Bayesian synthetic likelihood, which needs to generate a lot of simulations from one single parameter value. So as I mentioned before, we have these other three helper methods. So the first one is used to check whether the input values of the parameters you give to the model are, say, valid in a sense. For this simple example, I'm just checking whether the length of the input values is correct, which in this case is 3. Then you need to check, you have a method to check whether the output simulation the forward simulation perform correctly. For instance, this can be used if your forward simulate method can give some error sometimes, so you can, or like whether it can give some values which are not valid numerically. So you can use this to check whether this happened and signal it to the inference scheme. In this case, we assume the forward simulation works correctly all the time, so we return true all the times. So finally, you have this get output dimension method, which basically just returns the dimension of your model, of each forward simulation, actually. So let's now run this cell to instantiate or actually define the model class. And once I've done this, I can basically use this custom model, which I've defined, in the very same way as the default models I was using before. So you see again here, I'm defining a prior model, sorry, a prior for the parameters. I'm using a uniform prior again, and I'm using these priors to define my Ricker model. And then in the last line, I'm just calling the forward simulate method to show you how this works. And I'm using to generate a fake observation, which I will use later for the inference scheme. And here, this list here passes to the model, to the forward simulate method, the parameter values which you use for generating this fake observation. And then you have this number of forward simulations. I'm just using one here. So let's run this. And yeah, I'm just showing here the simulation which I obtained. You see, it has this kind of alternating time series behavior. Yeah, if your model is defined, for instance, in R, C++, or Fortran, of course, we provide ways to run models which are defined in this way. There are some examples in the documentation if you want to look at them. And it is a very similar fashion as the one I've described before. You can implement new statistics, classes, new distances, and so on. So basically, everything you need to do is to define a new class which defines some methods in the way they should be defined, let's say. Cool. So now I will have a look at another very useful feature of the ABCpy library, which is learning summary statistics. And in this example, I will use the semi-automatic approach by Farnell and Prango 2012, which is widely used. And I will use neural networks to learn the summary statistics. So when we use neural networks in ABCpy, ABCpy uses PyTorch in the background for handling the training and so on. So let's see how this is done. You see, this is actually quite easy. We have the semi-automatic NN class in ABCpy, which performs the semi-automatic neural network learning. And you need to import it from the library with this line, and you just instantiate it with this other line. And when you instantiate it, it will take care of generating the data and learning the neural network for you. So when you instantiate it, you need to pass to it the Ricker model, or I mean, in general, the model from which you want to generate data. You have to pass statistics, which you want, the statistics function which you want to apply to the data set before learning your automatic summary statistics. So let's say if you want to learn the summary statistics starting from a reduced set of statistics instead of the full data set, you can do that. In this case, I don't want to do that, so I just pass the identity. Then again, you need to pass this backend object, which just tells the ABCpy library how it should generate simulations, whether it should try parallelizing or not. And then you have some parameters which you can use for setting how the neural network is trained. For instance, in this case, I'm using 100 epochs, and I'm using no GPU speed up, let's say. So once the training is done, let's start running this actually. So this will take a little bit. You see now the neural network is training. It's taking a long time. Right, okay, not too long. So once this neural network training is done, you can use this method, getStatistics, to obtain from it the learn summary statistics. So while we wait for this, I just want to point out that in this case, I didn't explicitly specify which neural network I want to use. And if you do that, ABCpy will use a default neural network for you, which it will build from, let's say, considering the size of the parameters and of the model output. And if your neural network you want, of course, you can specify neural network which you want to use if you want to use, let's say, more complicated ones. And if your neural network is very large, you can use q=true for exploiting GPU for training, let's say. Besides this semi-automatic approach, we also provide distance learning-based approach, which we investigated in a paper last year in order to fit the neural networks. So let's now see how we can use this for performing inference. So we will try to perform inference with the Ricker model and the automatic summary statistics, which we used before. So you see, this is very similar to the first example I gave. The difference here is that the summary statistics have already been defined before. So I don't need to define them again, but I need to define the distance using the summary statistics, which I have. So next, again, I need to set the backend for parallelization. Still, for this example, I'm using no parallelization at all. And finally, I need to set the inference scheme. So for this example, I'm using the SMC-ABC scheme just to, just for the sake of varying a little bit from the rejection ABC. And I'm instantiating it in the same way as before by passing to it the model, the distance, and the backend, and finally a random seed. So next, you can call the sample method to sample from the model, and you need to pass to it the fake observation, which we defined before, the number of steps and the samples you want to get. So let's try to run this. So finally, actually, this full output equal 1 just means that in the journal file, I will store all simulations from each, or rather all inference results for each step of SMC-ABC. Right, so now this seems to have run correctly. I just want to point out that if you want to use, for instance, MPI parallelization, this is very easily done by just replacing backend dummy here with backend MPI. And if you do that, basically what happens is that for each particle in the SMC-ABC, it will be the forward simulation for each particle of the SMC-ABC will be executed on a different MPI thread or task, probably. Task is the right name. Cool. So now let's have a look at the posterior distribution we obtain in this case. I'm using the same method as before. And in this case, I'm asking to the method to just show the univariate marginals just for the sake of simplicity. And I'm setting a vertical green line to the value of the true parameter, which generated the data set by this parameter here. Cool. We also have some method in the journal file which is used to, for instance, investigate how the inference proceeded. So we have this plot ESS, which shows the effective sample size across SMC ABC iterations. So you see now we have that, as expected, the effective sample size decreases across SMC ABC iterations. Cool. So now my last example I want to show is how we can easily extend ABCpy library for testing new inference approaches. We use as a case study our recent work we have done with on performing likelihood-free inference with scoring rules. So just to introduce that, I will start recapping the Bayesian synthetic likelihood. Actually, we've seen this in the first talk. So yeah, I won't spend too much time on this. So as we've seen from the first talk, Bayesian synthetic likelihood just means in our we define a new posterior, which is the synthetic likelihood 1, which is of course proportional to the prior times a normal likelihood, where the normal likelihood has a mean vector and covariance matrix which depend on the parameter value theta. So in this case, okay, usually in synthetic likelihood approaches, people first compute the summary statistics and then compute the, let's say, define the posterior on the summary statistics space. For the sake of this example, I'm just assuming Y is the summary statistics space. So in synthetic likelihood, what people do is usually for, let's say, for a given value of theta, you generate some simulations from your model, and from them you estimate the mean and covariance matrix. And then you replace that in this expression and you evaluate the likelihood for your observation Y. In ABCpy, we implement this approach in the approximate likelihood class, as I mentioned before. And in this recent work, we have proposed this generalized Bayesian likelihood-free inference with scoring rules approach, which you see is quite similar to the synthetic likelihood 1. And again, we define a new posterior for our parameters, which is proportional to the prior times this term here, which is the exponential of minus some weight W times this scoring rule S of the distribution of the model at theta and the observation Y. So for the sake of this presentation, a scoring rule is just a function between a distribution, let's say the model distribution at a parameter value, and the observation. And similarly to Bayesian synthetic likelihood, we will use, let's say, an empirical estimator of this scoring rule by generating simulations from the model theta at theta values, at the parameter value theta, let's say. So you see, we have a similarity between these two approaches. What we have done with this new, let's say, newly proposed approach is just replacing the Gaussian log likelihood with this term inside the exponential. So basically what I want to do now is to use the inference capabilities of ABCpy for performing inference with my new, let's say, inference method I want to test. So the way we do this is basically we know ABCpy already has a way to perform inference with the Bayesian synthetic likelihood, which is a subset of this approximate likelihood 1. So what I do is I define an abstract class for these scoring rules, which subclasses the approximate likelihood 1. So yeah, just to put everyone on the same ground, an abstract class is just a way to set the methods or the functions that each scoring rule class will need to implement, as well as to set some common methods or common functions. So for instance, here you can see I'm defining this scoring rule class, which takes as an input, which subclasses the approximate likelihood class so that it inherits from it the methods approximate likelihood class implements. Yeah, so there you have an initialization function or method to which you need to pass a summary statistics calculator, as well as the weight W, which you want to use in the inference scheme. And then we have here we have two abstract methods. So these are the methods which each subclass of scoring rule which you need to implement. Otherwise, you are not allowed to instantiate any object of that class. You see here we have the score and score max methods which will need to be implemented by each actual scoring rule. So finally, as we want to, basically as in ABCpy, we have, for instance, MCMC scheme, which uses the log likelihood method of the approximate likelihood. We need to define the way to compute the log likelihood for this scoring rule. And if you look back at what I've written in the previous slide, the log likelihood for this scoring rule method is basically minus the weight times the score of the model. So you do that in this way. This is just a way to, let's say, alias the score method to log likelihood 1. So let's define this scoring rule class, and now we define an actual scoring rule class. So in this case, I'm using the energy score, which is a score you can use, and we use this. I mean, this is a subclass of the scoring rule class, abstract one, which I just defined before. So you see now, in this class, I need to implement the score and the maximum score methods. Otherwise, you are not allowed to instantiate any objects of this energy score class. So of course, you need to have an initialization method to which you need to pass the statistics calculator, the weight, which you use in the inference scheme, as well as the, in this case, we also have an additional parameter, which is some scalar number. So next you need to implement this score method, which takes as an input the observations and the simulations, and it estimates the energy score in this case. So you see we do the estimation by calling this helper function, which is defined down here. And finally, you need to define the maximum score method, which is in this case just infinity. So let's run this, and we have defined the class, and we can use it to perform inference. So we now instantiate a model and the scoring rule. For the sake of this example, I will use the GNK model. So I've defined the GNK model class somewhere else, just for the sake of brevity. But again, this is included in the ABCpy models repository I mentioned before. So again, I'm using a uniform prior for the parameters, and I'm defining the model with this line here. And I can very easily instantiate the scoring rule by this line. You see, it is very similar to what we used to do for the distances. And here I'm just passing the summary statistics calculator, as well as the weight I want to use in the inference. And once you do that, you can perform inference with MCMC. You see now.
Lorenzo, sorry, you have 2 minutes left.
Yeah. Okay. Thanks. Yeah. You can perform inference with MCMC. We are doing it now. I'm using 1,000 burning steps and 5,000 MCMC steps. And at each step of the MCMC, I'm using 100 samples to estimating my scoring rule. Right, so let's have a look at the posterior distribution which we obtained. In this case, you see it doesn't look great, but I've run a small number of MCMC steps for the sake of brevity. And yeah, actually, with this approach, you can also perform, let's say, inference with a large number of observations. And what we've noticed is that if you use the energy score rather than synthetic likelihood, when you increase the number of observations, your posterior concentrates around the true parameter value. While we noticed this did not happen with the synthetic likelihood. So I just thought this was quite interesting. But I couldn't reproduce this figure online because it's, of course, too costly to run all of these experiments. Right, so basically almost at the end of my presentation, I just want to point to useful resources people can find online. So first of all, we have this GitHub repository page where you can have a look at the code, you can download it, you can keep track of the updates we are doing. And of course, you are welcome to contribute if you want and to use the library. Again, we have a documentation page where we have some tutorials, we have some examples on how to do things. We report how to extend the library and so on. And finally, we have a paper which is due to appear in the Journal of Statistical Software. And in this paper, we focus in quite a lot of details on the parallelization structure of ABCpy. So you're welcome to read that if you're interested to learn more about that. Yeah, finally, to conclude my presentation, I want to thank all the people who contributed to ABCpy in some way. So Rita Bratatutta, who is my PhD supervisor, he is in the University of Warwick. He started the ABCpy library together with Marcel Schöngers, who is from Switzerland. And other contributors which contribute to essential parts of the library are Avinash, Nicole, and Pierre, and they contribute to, different parts of the library which are very essential. Yeah, so I think this is the end of my presentation. I hope I was inside the correct time. So thank you very much for listening. I hope you enjoyed.
Thanks, Lorenzo. Yes, you were exactly on time. So unfortunately, I've been asked to keep the time strictly, so we have to take